So we're going to discuss properties of acids and bases, and we're also going to go over one individual's early ideas of acids and bases. Okay, we're going to talk about a few different people. The one we'll talk about today, his name is Arrhenius. Okay, we'll talk about him. We'll talk about Bronsted and Lowry, two individuals who were doing similar research on acids and bases, but they weren't doing it together. And finally, later on, we'll talk about Lewis acids and bases. And it's just that they're different ideas that they had on what is an acid, what is a base. But we're going to start off our discussion today with just dealing on properties of acids and bases, and then we'll get into Arrhenius. Okay, when we discuss the properties of acids and bases, the very first one, aqueous solutions of acids have a sour taste. Now, what I mean there when I say never taste acids, okay, you're not going to look and say, okay, here's some clear liquid in this beaker. I wonder if it's an acid. Let me take a chug of it and see if it's sour. No, you're not going to do that, because if that's a concentrated hydrochloric acid, it will burn. It will burn. However, how many people have ever had lemonade? Okay? Orange juice. Okay? Citric fruits have citric acid. All right? How many people have ever had vinegar? I like putting vinegar on my French fries when I go to the fairs. Okay? Vinegar is acetic acid. Okay? So we do taste acids. However, when I say never taste an acid, I'm meaning do not determine whether it's an acid or not by taking a drink of it. Okay, we would never do anything like that, because that would be very dangerous. Acids change the color of acid-base indicators. I'm sure at one time or another, you folks have used something we call pH paper. Okay? pH paper is universal indicator. It has different ranges of colors for different pHs. There are many, many, many different indicators that you could use for acids and bases. Remember the lab where I did as a demo in which we used? All right, sweet. Remember the lab I did as a demo where we used food coloring as an indicator. Okay? You'll hear certain things like phenolphthalein. Phenolphthalein. That's an acid-base indicator. We'll talk about it later. You also hear about litmus paper. So acids will change the color of acid-base indicators. And we'll get into those later on. We'll probably do some labs with acid-base indicators. Some acids react with active metals to release hydrogen gas. I used to do a demo, I don't do it anymore, but I used to do one in which we took aluminum foil and reacted it with hydrochloric acid. Now, when we do this, you can see that on a single replacement reaction, if aluminum is strong enough, is more active than the hydrogen, it will replace it, which it actually does, and it gives us aluminum chloride and hydrogen gas. Now, realize that this is indeed a skeleton equation. I don't have that balanced, and I'm not going to balance it, but I was just showing you that aluminum chloride and hydrogen gas. when we have acids reacting with active metals. Acids react with bases to form neutralization reactions, which produce salt and water. Okay, that was one of your double replacement reactions. Okay, one of the double replacements, acids react with bases to produce salts and water. We have a specific name for that. We call that a neutralization reaction. And finally, acids conduct electricity. Remember when I showed you the conductivity? I had the bulb and the harness and I put them in the liquids. Okay, if I would put that bulb and harness into an acid, it would indeed light up the bulb. It does conduct electricity. Now, you don't need to write all of these down. If you want to get a couple of them down, that's fine. But I just listed for us some common acids. Citric acid has lemons and limes. Acetic acid is the main ingredient in vinegar. Lactic acid is in sour milk, and it's also produced by your muscles, okay? A byproduct of exercise. Tartaric acid is in grapes. Hydrochloric acid is the acid that's involved in your stomach. Ascorbic acid is in vitamin C. And finally, one of the most important, sulfuric acid. It's in fertilizers and dyes. It's one of the #1 produced chemicals in the world. So those are just some common acids and bases. You don't need, acids. You don't need to write all of them down. Just get a couple examples. Bases. You're going to see here with these properties of bases, ladies and gentlemen, that some of them are similar to what we just did with properties of acids. Aqueous solutions of bases taste bitter. Okay? They taste bitter. Now, once again, never taste bases. It's a common misconception that acids are very, very dangerous, but bases aren't. That is a misconception. If you have a strong base, it is equally as dangerous as a strong acid. Okay? Now, aqueous solutions taste bitter. Has anybody ever got soap in their mouth? Okay? Is that a very good taste? My mom used to do it if we'd say cuss words when we were little kids. Okay? That's how torture we got. She would take well, not even a bar of soap. She would squirt liquid soap into our mouth. Okay? But, once again, we should never taste bases. Bases change the color of acid-base indicators. We hit on some of those. Number 3, dilute aqueous solutions of bases feel slippery. Now, do you think that we should touch bases? No. No. But once again, well, how do we know this? Think back to that bar of soap. You pick that up any normal given day, not a big deal. When you take a shower and you get that all wet, what happens to it? Yeah, it's slippery, right? Because it's a base. It's a base. Bases react with acids to produce salts and water. Once again, that's the neutralization reaction. Finally, bases also conduct an electrical current. So what are some common bases that we deal with? Ammonia. Okay, I'm sure you've heard of ammonia. It has a very distinct smell. Lye is in drain cleaners. We just talked of milk of magnesia. We used that in the lab demo the other day. That is a laxative, give you the scoots if you're all bound up. And lime is another one. It's present in cement and plaster. So those are some common bases. Which leads us to Arrhenius. Arrhenius. Svante Arrhenius, 1859, 1927 was when his lifespan was going. Once again, I don't necessarily think that that's important to know when Arrhenius was around, okay? That's not as important to know when he was around, but what is important are his ideas of acids and bases. Now, Svante Arrhenius was a Swedish chemist. He did win a Nobel Prize for his work. Now, what Mr. Arrhenius said, we now call an Arrhenius acid. An Arrhenius acid is a compound containing hydrogen that forms hydrogen ions as the only positive ion when the compound is dissolved in water. Now you can see right here, and you look and say, well, where's the hydrogen ion? Okay, we have it wrapped up right here in this equation with the hydronium ion, H3O plus. Now, I want you to be aware, because this is written out as we have it right there, okay? Also, though, you will see this in times where we write it out, HCl, aqueous solution, will break down into H plus ions and Cl minus ions, and we just leave that water out of the equation. It's a little easier to see that hydrogen ion right now, okay? So we often write that top equation that I have typed out here, we often write this also as this, okay? And we're seeing that the same way, okay? It is splitting down, it is dissociating into its ions, the H plus and the Cl minus. And you're going to see later on that the amount of dissociation that occurs is going to be important with acids and bases. Okay? So an Arrhenius acid is a compound containing hydrogen that forms hydrogen ions as the only positive ion. As we're looking at these, we're giving names to different acids. Monoprotic, diprotic, triprotic. Okay? And all this simply is, if we have an hydrogen ion, okay, hydrogen has one proton, one electron. If we lose that electron, hydrogen becomes only a proton. So that's why we have monoprotic. One proton, right? One hydrogen. Diprotic. Okay, what do you think that is? Two hydrogens. So the diprotic acid, the example, sulfuric acid, H2SO4. Triprotic has three hydrogens, H3PO4. Now, what determines, we'll go way, way back in our learning, what determines whether we have one hydrogen, two hydrogens, or three hydrogens? What determines that? Look up there. You're right, Ethan. Charge of what? Why do we only have one hydrogen here? Because Cl is 1 minus. Why do we have 2 here? SO4 is 2 minus. Why do we have 3 here? Because PO4 is 3 minus. Okay? So that determines whether it's a monoprotic, diprotic, or triprotic. Now, this is the last slide we're going to cover today. It is dealing with what is an Arrhenius base. Svante Arrhenius, here is his definition of a base. An Arrhenius base is a compound that form hydrogen ions as the only negative ion when dissolving in water. So here I have sodium hydroxide. If I make an aqueous solution of sodium hydroxide, I get Na plus ions and I get OH minus ions. So Arrhenius said, this indeed is a base, because bases form hydroxide ions when they are dissociated in water. Okay. So today, what we have learned, we've learned some basic properties of acids and bases. We've learned some examples of what is an acid, what is a base. And finally, we talked about our first scientist concerning acid bases, Svante Arrhenius, and we've talked about, okay, what is his ideas? What were Arrhenius's ideas of an acid? Well, he said they have hydrogen ions. What were his ideas of a base? They broke down, they dissociated into hydroxide ions.